Hi, I'm John McAllis, a software developer at Intel, and I'm going to talk to you about blur filters. Image blur filters are typically seen in graphics. Depth of field, HDR Bloom, and other post-processing effects are common to 3D engines and other graphics applications. On the surface, blurring an image seems simple. Average neighboring pixels, and you get a new value. Of course, describing it that way makes it sound easy, but there are different methods for doing so, with differing results, quality, and performance. We'll focus on the trade-off between quality and performance. I'll emphasize performance for two reasons. First, the difference in compute cost between a simple and an optimal algorithm can be an order of magnitude. Second, different algorithms might be optimal on different hardware. While generic algorithms can oftentimes be easier to understand, implement, use, and maintain, there are cases where a specialized one can do a better job. For an example of this, follow the link below. The algorithms I'll discuss can also apply to other effects. Let's start with the Gaussian blur. This is a common filter for reducing image detail and noise, and it's the go-to filter for simulating a lens going out of focus. It's called the Gaussian blur because it uses the Gaussian curve. A common way of implementing Gaussian blur is through the convolution kernel. This means that each pixel's new filtered value is calculated by constructing a two-dimensional matrix of values, then calculating the weighted sum of all neighboring pixels. The problem with this approach is that the complexity grows exponentially with the kernel size. However, this can instead be calculated as two vectors, which means the filter can be done in two passes, horizontal and vertical. Each pass has a complexity equal to the kernel size rather than the square of the kernel size. This greatly reduces the calculation time while arriving at the exact same result. It is useful to note that this algorithm can be used for any other convolution filter, such as edge detection or sharpening. Using a real-world scenario, this algorithm works great for desktop and even newer mobile GPUs, processing the 1280 by 720 frame in milliseconds. But saving milliseconds can mean the difference between a sub-25 frame rate game and a game with 30+ frames per second. With fixed function GPUs, like samplers, we can load the value of two neighboring pixels and return the interpolated result for the cost of one texture read. This halves the shader instructions and increases performance by a factor of 2. However, there is a memory issue with larger kernels that can diminish this result. This was an overview of the Gaussian blur. See our other videos for additional methods.